This week we're focused on nuclear magnetic resonance, or NMR. This is a very widely used analytic tool to analyze samples. It's used in industry, and you'll be using it a lot in Orgo 2 lab. So NMR is actually used in MRI, or magnetic resonance imaging. Oh, that should say imaging, not imagine. But an MRI is widely used in the medical field, and that provides details about soft tissue. It's a similar process as what we're doing in lab as NMR. You use magnetic fields and radio waves to analyze the composition of soft tissue. So when you take an MRI, there's a large magnet and then radio waves that soft tissue is exposed to. And so the shading of an MRI image provides information about the makeup of the tissue. So I have an example of an X-ray and an MRI of a knee. So here you can see, let me get my laser pointer. In the X-ray, you can see knee bones. In the MRI, it provides a little bit more detail about the tissue around the bones, and a little bit more detail right here. Those dark pieces are actually tendons. So that's the ACL and the PCL there. So MRIs, super useful in the medical field, and MRIs are based on essentially NMR. So we're going to learn about very specific nuclear magnetic resonance for both protons, hydrogen atoms, and carbon atoms. And the reason this works is because all nuclei, which are made of protons and neutrons, they spin. And since in the nuclei we have charged particles, we have protons, that when those spin, that induces a magnetic field. So protons and neutrons, the nuclei, are always spinning. So as they spin, which is kind of shown here, you can imagine a nucleus spinning on an axis. It generates this magnetic field. Let me try to get a pen now, where we have kind of, just like we think about around the Earth, around a magnet, there's a magnetic field. We have a North Pole and a South Pole around the nucleus of an atom. So the spins of a nucleus can be affected by an externally applied magnetic field. So if you situate protons in a magnetic field, that'll impact their spin, because now you have something with magnetic north and south poles with a magnetic field being exposed to another larger field. So when a magnetic field is applied, protons will arrange to have spins either parallel or anti-parallel to the magnetic field. So if you imagine a sample of molecules, protons or nuclei are just arranged randomly, spinning in random directions. You then apply a magnetic field, and in this image, the direction north to south is pointing up. Then these nuclei will arrange to either be aligned with the magnetic field or anti to the magnetic field. The nuclei that are anti-parallel to the applied magnetic field exist at a higher energy state. And so that's exploited when we do NMR analysis. So thinking about, in this image, we have the energy of nuclei, energy of anti-parallel spins are pink, and then the energy of parallel spins are blue. As you increase the strength of the magnetic field, the difference in energy levels increases. So a stronger magnetic field, you'll have a greater difference between these two energy states. If the magnetic field is 0, the two energy states are equal to each other in energy. So with a strong magnet, we can increase the difference in energy between anti-parallel spins and parallel spins. So that means you have some nuclei that are existing at this lower energy state with parallel spins, and some that are existing or can exist at this higher energy anti-parallel state. If your sample is then exposed to radio waves, the nuclei that are at the lower energy can absorb a specific energy, specific wavelength of energy to then exist at the higher energy state. So in this way, it's very similar to the different, the other analysis techniques we've looked at, where molecules will absorb energy of a certain wavelength, and we detect the energy that is absorbed or the energy really that's not absorbed, and that tells us what the molecule does absorb. So when we're looking at NMR, the difference in energy between the parallel and anti-parallel states is generally within the radio wave frequency. And so after we've applied the magnetic field and exposed the sample to radio waves, the NMR instrument can then detect which frequency of radio waves are absorbed by the sample, and that will tell you about the nuclei that are present in the sample. So the next image that I have on the next slide kind of shows this in a different way. So we've got randomly oriented nuclei. They're all generally of equal energy. We apply a magnetic field. We now have some nuclei that are aligned with a magnetic field in a plus state. We have some that are anti-parallel to the magnetic field in a minus state. So we have lower energy aligned with magnetic field, higher energy anti to the magnetic field. And then when you add radiation in the radio wave frequency, nuclei that are at the lower energy state, so the +1/2, can then absorb that energy to be at the -1/2. And so an NMR spectrum will tell you the energy that's absorbed by protons or by nuclei in the sample, and different nuclei that are in different bonding patterns in different chemical environments will absorb different energy waves. So I have an example of an NMR spectrum on the next slide for a molecule. First, I'll say that TMS is something that's often used as a reference point. It's a molecule that shows a peak at 0. So you can always make sure your instrument is working properly and aligned at 0. And so this is a proton, so an HNMR sample. HNMR, carbon NMR are both very common. Others are possible, and you'll learn about that in the videos that you watch. But in our class, and in, I believe in Orgo 2, you'll only focus on proton and carbon NMR. But this is an example NMR spectrum of a molecule that has protons, 2 hydrogen atoms in 2 different chemical environments. So we have 2 different peaks. This is just that reference sample, so that's not involved, or that's not part of the molecule that's being analyzed. But we have protons in 2 different chemical environments, and so we get 2 different peaks. The location on the x-axis tells us information about the chemical environment that they're in. And the integration, which is not shown on here, we'll talk about that a little bit later. That also gives you some information.